Hello and welcome to this video in which I model and solve work problems. Okay, so this is I'm just going to be doing a couple examples where we're dealing with the amount of work someone does, and that work will change from problem to problem. You'll see in one problem the job being worked on is assembling notebooks for attendees at a conference. And in another problem, the work being done is the work being done to seal a driveway. Right? And I'll write out that we're going to be working on when I talk about work. These are work problems at which for which people are working at a constant rate. Right? Meaning that they're doing the same amount of the job for every unit of time. Right? They're always doing a fifth of the job every hour, or they're always doing a third of a job every hour. And that never changes. Okay, so this is going to be kind of pretty simple work problems, no calculus involved or anything, just some algebra. And we're also, because we're dealing with constant rate work problems here, we're going to be dealing with the simple principle that the amount of work that is done is equivalent to the rate at which you do it. And again, rate is just short, it's like ratio, right? Rate, ratio, ratio, rate. So the amount of work that you do is equal to the rate at which you work, the speed at which you work, multiplied by the time that you work for. All right. So if I do, a third of a job in an hour, and I work for 2 hours, that's your rate, job per hour, a third of the job per hour, times 2 hours, that's 2/3 of the job done. Alright, so we'll work with that very simple principle on these couple word problems. Alright, so let's begin. Alright, so again, I just pulled both of these from some book I got. Alright, so the first one here, it takes Molly 6 hours to assemble notebooks for attendees at an educational technology conference. It takes Jacqueline, or Jacqueline, let's say Jacqueline. It takes Jacqueline 3 hours to do the same job, right? So to assemble the same amount of notebooks that are provided for these, for this educational technology conference. Working together, right? So Molly and Jacqueline together. Working together, how long does it take Molly and Jacqueline to assemble the conference notebooks? All right. So throughout this problem here, one job, when I write one job, that'll mean assembling all the conference notebooks. Okay. Alright, so I read through the problem, and just like any other word problem, I read through it and I say, what do they want? What are they asking me for? What are some things I don't know? Alright. The question is, how long does it take Molly and Jacqueline to assemble the conference notebooks together, right? So this entire thing is what they're asking for. So I'm going to call that something. Now it's how long, so it's a question of time. So off to the side here, I'm going to let like just a lowercase t, usually represents time in a lot of problems. So I'm going to let lowercase t represent the time in hours, right? Because all the other times that are given are in hours, 6 hours, 3 hours. So let's say this is the time in hours it takes them, right, both Molly and Jacqueline, to do the job, assemble the conference notebooks. Again, when I say job in this problem, it's assemble all the conference notebooks. So t, lowercase t here, will represent the time it takes them to do the job together. Alright. And as I mentioned at the opening screen of this video, we're working on this a very simple principle throughout these problems. It's the work that you do is equivalent to the rate at which you work at, right? How much of the job you do per hour, or how much of the work you do per minute or per day or whatever. This is the speed at which you work multiplied by the time that you work for. All right, so every single thing I do in these couple examples I've got for you are going to rely on this principle. All right, so I'm trying to find this t, right, how long it takes them to do the job together, but I only have information about what they do separately. All right, so I'm going to work on a few equations here, you'll see, where we work on things on Molly and Jacqueline separately, and it involves, this principle. So let's talk about Molly first. Right. So Molly, now we know she can do the entire job, right? She can do one job, assembling the notebooks, in 6 hours. If she works for 6 hours, she get one whole job done. So applying that to here, the work she would do is one whole job. Right? She does the whole job, would be equal to. Now the rate at which she works we'll figure out really quickly in a second, but I don't know what that is right yet. I don't know how fast she's working. I just know the time it takes, right? So I'm going to call the rate at which she works a lowercase r with a subscript of m, because I'm going to be doing this for Jacqueline as well, and them together. Right? I'm going to have 3 of these lowercase r. So you see this very often in math, where there's you're seeing the same variable again, but there's a subscript implying that it's something different. So r with a subscript of m, I'll have that represent the rate at which Molly works. Okay, so back in my equation involving Molly, she can complete a whole job, and that'll be, the work she does is one job. The rate at which she works at, I'm calling this r sub m, and multiplied by the time she works for to complete the one job. They said earlier in the problem is 6 hours. It takes her 6 hours to complete this one job. All right, so you see, like I said, very quickly. And if you want to write hours here, fine. I'm just, you don't have to fill in words a lot of the times in an equation. But I'm going to keep the units there for purposes of talking about the rate. So you can see hopefully very quickly that we can solve for this r sub m. I would just simply have to divide by 6, this 6 hours here. So taking this down here, we can see the rate at which Molly works is 1/6, right? 1/6, and you had job in the numerator per hour in the denominator, right? So this isn't the answer, I'm just bubbling it, all right? But this is the speed at which Molly works. She does 1/6 of the job in an hour, right? 1/6 of a job per hour. So, that means that 6 hours she'd do the whole job, exactly what they said. Okay, so there's the speed, the rate at which Molly works. And I'm going to do something similar for Jacqueline. Alright, so let's push this up a bit. Alright, so now we're going to talk about Jacqueline. Alright, so same deal. Using this same principle throughout the problem. The work Jacqueline does, or in the information given to us, they say it takes Jacqueline 3 hours to do the same job. So that job of assembling the conference notebooks. So for her, the work done one job, the assembling all the conference notebooks, would be equal to the rate at which she works at. Now again, that's something I don't know, but we'll figure it out real quickly. I'll call that R for rate. but then this time with a subscript of j, right? And again, you can call these whatever you want. I'm just doing this for, you know, the rate at which Jacqueline works. You can call it whatever you want, all right? But I prefer this. So this r sub j, I'm going to call this is the rate at which Jacqueline works. All right. So I'm going to pop that in my formula here, right? You know, the work she did is one job, and that's equal to the speed that she works at is this r sub j, I'm calling it, multiplied by the time it takes her to complete that work. The time it takes her to complete one job is, you know, in the problem here they mentioned 3 hours, right? It takes her 3 hours to do the same job. Again, you can write hours if you want, but, you know, not really necessary. And then same thing, kind of like how we found the rate at which Molly works, we can now very easily see the rate at which Jacqueline works, just dividing by 3 hours here. So the rate at which Jacqueline works is, you know, 1 divided by 3, or 1/3, and then you add, you know, job in the numerator, right, the one job, and then hours in the denominator. So she works at a rate, and again, this isn't the answer or anything, this is just her speed, I'm just bubbling it. So she works at a rate of 1/3 of a job per hour. All right, so if you gave her an hour, just 1 hour, she'd only get 1/3 of the job done, right? Thus it would take her 3 hours to complete it, right? Okay. So that's the rate at which Molly works, right? 1/6 of the job per hour. That's the rate at which Jacqueline works, 1/3 of the job per hour. Now we can talk about, finally, what if they worked on the job together? All right, so here we go. New line where we talk about them working together. All right, and that's a pretty light marker. I'm going to get rid of this. All right. So them working on the job together. So again, I want the same principle. I'm going to set up something like this. Now, let's say they completed this one job, right? So the one job, the assembling of the notebooks equals, all right? And then here, I don't know. I know how fast they work individually. I don't know how fast they work together. But we can use how fast they work individually to figure out how fast they work together. And that's where this is going to come in. So the rate at which they both work, I'm going to call that R with a subscript of T for together. All right, this is the rate at which they work together. Then I'm hoping this makes sense. The rate at which they work together is simply the sum of the rates at which they work separately. The rate at which they work together is just the rate at which Molly works plus the rate at which Jacqueline works. All right? Hopefully that makes sense, right? Think about it. If she does, 1/6 of the job in an hour, and she does 1/3 of the job in an hour, if I gave them, say, 1 hour, she'd get 1/6 of it done, she'd get 1/3 of it done, so they'd get it, 1/6 plus 1/3 of it done, together. You'd be adding those up. Or if I just talked about plain old numbers, right, nice whole numbers, say for instance, say Molly could assemble 5 notebooks in an hour, and Jacqueline could assemble 3 notebooks in an hour. Well, then in an hour, Molly would have done 5, Jacqueline would have done 3. Together they would have done 8 notebooks in an hour. It's just taking their sum. All right, so the rate at which they do the job together is, well, Molly's rate was 1/6 of the job per hour, so let's put 1/6, and just know that this is jobs per hour, plus, and then the rate at which Jacqueline worked was 1/3 of the job per hour. All right, we're almost done getting the rate at which they work together. And this is 1/6. Then, when you add fractions, you need a common denominator. 1/6 plus, and then, I would multiply this fraction here by 2 over 2 to get a common denominator of 6, right? The least common denominator would be 6. And that'd be 1/6 plus 2/6, right? That's the same as a third. And then once the denominators are the same, that's the denominator of the sum, and you just add the numerators. 1 plus 2 is 3. And 3/6 reduces to 1/2. And remember, all these are rates. All these have this unit of jobs per hour, right? So this is important, right? This is going to help us a lot because it says that, so I actually do, I said I didn't know the rate at which they work together, but since I know how fast they work individually, I actually do know how fast they work together. So if they work together, they'd get half the job done in 1 hour. So hopefully you can see that means they'd be done in 2 hours, but let's finish the problem. Let's finish out our principle. So again, I'm working on this work equals rate times time principle. So the work they're doing is the whole job, assembling all the notebooks. That's equal to the rate. I have the rate. That's this half a job per hour down here. So the one job equals, and then half the job per hour. Again, if you want to put the units in, that's not wrong. It's just, usually it's not done. Multiplied by, and then the time. How long does it take them to work together to finish this one job? That was the question. Remember, that was the question posed by the problem. How long did it take them to do it together? And we called that lowercase t, right? That would be t hours. And maybe you see some, you talked about, if you've seen unit cancellation before, I'd have, the hours here canceling with hours there. And then when I divide by a half here in a second, we're going to get rid of the jobs, job over here divided by job there. So really I'm just working with a thing in numbers. Alright, so really I'm solving this equation. So now we're solving, I've got 1 on this side for the one job equals, the half times t, or half of t. And that's it, right? Getting rid of all the units would eventually cancel here. And let's see what happens. This is an easy one to solve. If I'm, I would just need to, divide by a half, but, division by a half is the same as multiplication by 2. So multiply both sides by 2. And there we have it. We have t, this side be t, I'm just throwing it on the left, equals 2 times 1 on the other side. 2 times 1 is 2. And again, double check, yeah, that works. Half of 2 is 1. This actually works out. Now this isn't the answer totally, right? I mean, this is the number representing the answer, but it is a word problem. You should answer word problems, with questions in complete sentences, with units. So remember what t represented, right? It was the time it took them to do the job together in hours. So after all this, right, finding all these rates and figuring out how they do it together, we have determined that it takes them 2 hours to do the job together. So that is actually how I would answer the question, right? So my full and complete answer would be, I would say it takes, now you can write Molly and Jacqueline, but I would just say, let's say it takes them 2 hours, right? Again, you should have units involved, right? Make the number mean something for the problem. It takes them 2 hours to assemble the conference notebooks, or to do the job, because I did say the job earlier was assembling these notebooks, but I'll finish it off, right, to assemble the conference notebooks. Alright, so this here, and put in the box here, that is how I would answer this question if I were asked it, in a math class or an exercise, in a homework exercise or something. All right, and you should do that for any word problem, right? Answer in complete sentences, and make sure units are involved so that the numbers actually have meaning. Okay, great. And this whole time, right, throughout this entire process, I talked about each individual working, then we talked about them working together, and a lot of these work problems with constant rates of work are like this, where you have 2 individuals working on something, and then they talk about what they do together. And each time I'm continually using this principle that the amount of work done by someone or some group of people is equal to the speed at which they work multiplied by the time that they work for. Alright, so I'm going to continue on with this. I got one more example where we do something similar. Now this time I have this. It says it takes Leon, and you know he's a professional, 5 hours to seal his driveway working by himself. So Leon takes 5 hours to seal his driveway working by himself. If Michael helps Leon, right, so they work together, they can seal the driveway in 2 hours. So it takes them 2 hours to work on this thing, seal the driveway, finish the job together. Then the question becomes, how long would it take Michael to seal the driveway alone, right, by himself? So this is a very similar problem to the previous one, where I had these two individuals working on something, Leon and Michael, you know, just like Molly and Jacqueline. And then I have them also mentioning them working together, right, Michael helping Leon. So I'm going to do the same thing I did with the last problem, where I look at them individually. Well, I'm going to look at Leon by himself because they gave me information about that. Then I'm going to look at Michael and Leon together because they actually gave me information about that. And then the last part is, you know, what they asked me about. I'm going to look at Michael by himself. Okay, so in this particular problem, when I mention one job, that one job being done here is, you know, sealing the driveway. Okay, so anytime I mention the job, I'm talking about this driveway that's being sealed, right? Sealing the driveway. All right, so the first person mentioned, the first information given to me is about just Leon on his own, right? And still using this same principle that the work done by someone or some group of people is equal to the rate at which they work at multiplied by the time that they work for. Okay, so for Leon, you know, he can do this whole job. So I got one job replacing the work he's doing. He can seal the driveway, the one job equals, you know, the rate at which he does it at. And you know, again, I don't know what this is. I don't know how fast he works. I don't have a rate. So I call that R sub L, just like I did with the Jacqueline and Molly stuff. The rate at which Leon works, L for Leon. All right, so I'll even write that here. This is the rate at which Leon works. Okay, so I got this one job equals the rate at which Leon works. I'm calling this R sub L multiplied by the time that he can do the job in. Right, the time it takes him to do this one job of sealing the driveway is 5 hours. Right, they mentioned 5 hours, so times 5, and then hopefully you can see again that from this I can very quickly find the unknown, right, the rate at which Leon works. I guess I should have put hours here. It doesn't really matter. You don't have to put the units as long as you make sure you know what the units are. Keep it in your head. But I would just simply divide by 5 here and see that 1 over 5, you know, 1/5 is the rate at which he works, and that's jobs per hour, right? Job in the numerator, per hour in the denominator. So the rate at which Leon works, he does 1/5 of the job. He seals 1/5 of this driveway in 1 hour. That's what that means. So that would obviously mean that would take him 5 hours to do the whole 5/5, right? The whole job in total. All right, and hopefully you can see that, you know, that right away there. You know, you got 1/5 of a job per hour. That's done by Leon. Now, the other piece of information that they actually give us is about what happens when they work together. So I'm going to do that next. I'm going to make a line talking about that next. So what happens when they work on this thing together? So they seal the driveway, so they complete, you know, this one job. And again, I don't know the rate, right? The work they did is this one job. The work they did is, you know, sealing the driveway. I don't know the rate. So again, I'm going to call that little r for rate, and then with a subscript of t for together. So the rate at which they the rate at which they seal the driveway, or the rate at which they work together, is going to be called r sub t. Okay, and I don't know this, and I can't find this like I could in the previous problem, right? So I'm just going to call that, well, I can find it in a second, you'll see, but so that's, the rate is going to be r sub t, the rate at which they work together, multiplied by the time it takes them to do this work, right? The time it takes them to complete this job, to seal this driveway together, is 2 hours, right, from this second sentence. Times 2, and then again, if you want to write the units, fine. So from this, I can see the rate at which they work together. All right, I would just simply, to solve for this RT, R sub t, I would divide by the 2 hours, and you'd have 1 divided by 2, right? So half, and then numerator jobs, denominator hours, jobs per hour. Right? All right, so Leon by himself can do 1/5 of a job in an hour, right? 1/5 of the job per hour. When they work together, they seal half the driveway in an hour, right? They do half the job per hour, meaning they'll finish it in 2 hours, right? If they do half the driveway in 1 hour, they'll do 2 halves in 2 hours, right? The whole job. 2 halves is just one whole job. All right, so I've got that stuff. Now let's talk about Michael on his own, right? Now I should have probably done this ahead of time, right? But the question was this here, right? What they asked for is, how long would it take Michael to seal the driveway alone? So just like most word problems, I should have done this earlier. I apologize. I did it first with the last example. So this is a question of how long. So that'll be a time. So just like the last example, I'm going to say let's let lowercase t. Let's let that represent the time it would take just Michael, to seal the driveway. And every other time is in hours, so this is the time in hours it would take Michael, right, just Michael alone, to seal the driveway. Alright, so now I've talked about Leon with the information they gave me. I talked about what it looks like when they're working together with the information they gave me. Now I'm going to talk about Michael on his own. Again, using this same principle, work equals rate times time. Alright, so Michael, he does the driveway. Alright, so he completes this one job. So that's the work he did, right? The work on the left side there. Now the rate at which Michael works, I do not know this. Right, so again, I'm going to call this something. R sub m for rate of Michael, right? This will be the rate at which Michael works. Now, very similar to the last problem. Remember from the last problem, the rate at which people work together is simply the sum of all their individual rates. Right? The speed at which they can seal the driveway together, right, that RT, is just how fast Michael works plus how fast Leon works. Right? If Leon can seal 3 square feet in an hour, and Michael can seal 8 square feet in an hour, then after an hour they'd have done 11. You just add them up, 3 plus 8. It's the same thing with these speeds. So the rate at which they work together is equal to the rate at which Leon works, so that was RL, plus the rate at which Michael works. So the way they do it together is, the sum of the speed at which they do it together is the sum of the speeds that they do it individually. Hopefully that makes sense. Again, it was the same thing in the last example. So I can actually figure out what this speed at which Michael works is, right? Because I know RL, I know RT, so I can find RM. So let's do that. All right. So RT, the rate at which they work together, that was found on the previous page, that's half a job per hour. And again, I'm not going to put the units, but just know that it's the job, half a job per hour, equals the rate at which Leon works. We got that earlier too. That was a fifth of the job per hour. And then that's going to be added to the rate at which Michael works by himself. Again, I don't know what, I'm just going to keep calling it RM. Alright, then I would just simply subtract the fifth, right? We can solve this for RM. So RM, the rate at which Michael works, is 1/2 minus 1/5. And if you get the least common multiple of the denominators would be 10. I'd multiply this fraction by 5/5, giving me 5/10, right? That's a half. Multiply this by 2/2, giving me 2/10, that's a fifth. And now that they have the same denominator, right, that's the denominator of the difference, and then I just subtract the numerators. 3/10 of a job per hour. All right. So here's Michael's rate of speed at which he works. He completes 3/10 of the job in an hour. Right? So after 2 hours, he'd be done with 6/10, and then after 3 hours, he'd be done with 9/10 of the job, almost done. So it feels like he'd be done with the job in a little over 3 hours on his own, and let's figure that out. So back to this work equals rate times time principle with just Michael now. The work he's doing is the whole job, the sealing the driveway, one job. The rate at which he works, is this RM, but I know what that is now. That's 3/10. So here I've got the 3/10 of the job per hour multiplied by the time at which he works, and that was the question, right? That I have it underlined up here. How long would it take Michael to seal the driveway alone? That's this time, and I called that T, right? Times T hours. Again, hopefully you're seeing the unit cancellations here, right? Hours and hours over here, and I'd eventually divide by this 3/10 of a job, and then the jobs would cancel. Okay, I can get rid of all the units, and then we're just basically solving, bringing this down here, we're just solving this equation for T. 1 on the left equals, and then 3/10 times T on the right. Okay. Yeah, and this is pretty simple to solve. You can get rid of the denominators. Multiply by 10. So I'd have 10 on the left equals, and then when I multiply by 10, the 10's cancel over here. I'd have 3 in the numerator times T still, and then divide by 3, or you could just multiply by 10/3 on both sides, and I get T equals 10/3. And double check that. When T is 10/3, 3/10 times 10/3 would indeed be 1. So this is the solution. It's just, again, that's not how I'm going to answer the question. All right. The question, it's a word problem. You should answer word problems in complete sentences and have units so that the numbers have meaning. So the way I would answer this, I would say it would, it would take Michael, so it would take Michael, 10/3 hours. Remember this. Well, remember what T represented. It represented times and hours. Or 3 1/3 hours, if you want to write it as a mixed number, or 3 hours, and 1/3 of an hour is 20 minutes. 3 hours and 20 minutes. Whatever. All these are the same. So I would just say 10/3 hours. It has the same meaning as 3 1/3 hours or 3 hours and 20 minutes. It would take Michael 10/3 hours to seal the driveway. Alone. Right. And there. This right here is how I would answer this question in a complete sentence where numbers have units attached so that it gives them meaning. And there, I am finished with this. And you'll see, again, a lot of constant rate work problems are like this, where you have 2 individuals or 2 groups working on something and then working on it together, and you just determine, how fast could they do it together, or if you know how fast they do it together, how fast could one of them do it separately. They're all a lot of work problems you'll see when you're dealing with constant rates of work are like this. And just keep in mind this principle. This is huge. The work that's done is equal to the rate that you work at, the speed at which you work multiplied by the time that you work for. That's not changing. All right. Alright, so that's just it for today. A couple examples of that. And as always, at the end of these, I like to say, try your best, try the best you can to understand the material on your own, get the material on your own before you go looking for help. Because I just find that people tend to remember things better. It tends to stick with them more if they've taken the time and effort to work on something until they got it on their own. They feel more proud of it. So read the material, of course, right? Read the author's examples. Sometimes even try to work on the examples. See if you can do them before you read the author's answers for those examples the way he did them, or she, or they, sorry. And then you might learn from your mistakes that way. Practice problems, of course, exercises in the backs of sections. Look for the answers somewhere, and just to be able to check yourself. And don't just give up after the first attempt. Keep at it. If after several attempts of a problem it's still not clicking, things still aren't working, walk away from it for a bit, relax, de-stress, or maybe even, I would recommend going back and reading the material again, maybe even a third time, because maybe there's something you missed the first time, or maybe a second or third read through you'll see something will click that didn't the first time, especially after having worked on a few problems. But if after several read-throughs of the material, several attempts at problems, you're still not getting it, it is not a sign of weakness whatsoever to go out looking for help. That is what other people are there for. So ask a teacher, ask a tutor, a friend, someone you know in your class that has the material down and is willing to help. Look for supplemental materials online. Look for videos on the subject, maybe such as this one, or other videos out there, I assure you, that are much better than this. I promise you they're out there, but you can find them. And just keep at it. Stay persistent. Keep practicing. Don't give up, and I'm sure you'll get it eventually. And try to go into it with a positive mindset as well. If you constantly say to yourself that you hate math, I've always hated math, well, you're going to keep hating it. It's not gonna that won't change unless you change it yourself. Go into your exercises, go into your homeworks, go into your readings with a positive attitude and an open mind, thinking, hey, I might learn something from this someday. I enjoy learning this. I'm enjoying this. I can have fun with this, and you'll be amazed at the difference that I could make. Alright, so keep at it, keep practicing, try to have fun with it, and thanks for watching.